Hello everyone, today we will talk about our presentation, which is the application of linear algebra in science and engineering. This presentation is for the class of linear algebra. We will talk especially in the least squares problem in artificial intelligence. Our group members are Kenji Terencio, Zen Jinwo, and me, Lashi Muhammad Amin. First, we will talk about the foundation concepts in linear algebra. First, vectors and spaces. We know that vectors live in spaces. So we have a vector in R2 means it is one-dimensional or two-dimensional vector only. Yeah. Second, matrices. Matrices are two-dimensional vectors. Transformation is the function that maps into them. 3. Rank and independence. Rank measures independent row and columns, determines if linear systems have a unique solution or not, or only the trivial solution. Fourth, orthogonality. Perpendicular vectors with zero dot product, foundation for projection and least squares. And this is the most important thing for our topic. The dot product is not like the multiplication. If we have vector A and the vector B, vector A contains A1, A2, A3, and B contains B1, B2, B3. The dot product will be A1 times B1 plus A2 times B2 plus A3 times B3. But in the multiplication, we can't do this directly. We need first to do the transpose matrix of B to do that, because we need that the number of columns in A equals to the number of rows in B. But in dot product, it's not that much important.
Where does the least square problem emerge? This slide isn't just about math. It's about why we need this math in the real world, especially in artificial intelligence and data science. The first part is the goal in AI. In AI, our fundamental task is prediction. We have input information called features of or X, and we want to predict an output called Y. And then the linear model. How do we model the relationship between X and Y? We could choose a very complex model, but the simplest and the most interpretable is a linear model. The equation you see here is y equals w1 times x1 plus w2 times x2 plus blah 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 plus wm times xm plus b. As you can see here, this y is called our predicted output. For w, these are called weights. They tell us how important each feature is. For the x are the features. And then the b one. B is the bias term. It's like the starting value when all features are 0. And then the challenge. Find optimal weight and bias that minimize the difference between predicted y and actual y value. Look at this graph. We have actual data points and a line representing our model. The vertical distances between the points and the lines are errors, sometimes called residuals. As you can see, these lines all over around here. We want a line that minimizes these errors overall, but we can just add them up. Positives and negatives might cancel. We need a systematic way to measure total error. And then the solution. This brings us to the mathematical formulation. We want to minimize the difference between predicted and actual values in a structured way. That structured way is exactly what we call the least square problems. It's a mathematical foundation for finding the best fitting linear model. From scalar to vector, defining the model. The first one is batch processing. In real AI and data science, we never train a model on just one example. Instead, we use a batch of data, many examples at once. This makes the model more stable and accurate. And then, factorization. To handle batches efficiently, we factorize the model instead of writing many separate equations like this. We combine everything into one clean matrix equation as this one. So it will be more simple than in the slide 4. And then design matrix X. Here X is called the design matrix. Each row is one data point. Each column is one feature. Columns might be elapsed time, distance run, score, and etc. We also add a column of all ones to account for the bias term B. And then weight vector W. The vector W contains all the model parameters. These are the weights for each feature, plus the bias. Learning the model means finding the best weight. And then last one is loss function. Now how do we measure how good our model is? We define a loss function as this one. This is the Euclidean norm, the length of the error factor. It's the mathematical version of total prediction error. Look at this data table on the slide. Each row is an example. Each column becomes a column in X. One column, like point vector, is our target Y. So the table is literally X and Y in raw form.
Now, what we want is to minimize this loss function. And to make other things look more clearly, we change this function into this one. Just change the letter. And AX, as we all know, is a vector. Is any vector in the column space of A, because X is not fixed and A is a fixed, so the column space is a fixed one, and the vector AX is a moving vector in the column space of A, and the target Y is also a fixed vector, and you can see it here. And what we want is the length of the vector AX minus Y is the vector here. So obviously, the length of the vector AX minus Y, which is minimum when and only when the vector AX minus Y is orthogonal to the column space of A. Then we can get equation here. The transform of A multiply the vector AX minus Y equals to 0 because the vector is orthogonal to the column space of A. So we get this expression, and then we get this one. And if the transform of A multiply A, this matrix is invertible. We can multiply the inverse of the transform of A multiply A in the left side of both sides of the equation, and we can get the vector X equals to this one. And this one is just the solution of the least square problem. We've mentioned before that The solution of the least square problem is correct if and only if this matrix is invertible. So we get another problem. When is this matrix invertible? The answer is it is invertible if and only if the rank of A equals to the number of its columns. And now we'll provide the proof. As we all know, a matrix is invertible if and only if the determinant of the matrix does not equal to 0. And it just means the rank of the matrix equals to the number of its columns. Since we know that the rank of it equals to the rank of A, and we get that we need to make the rank of A equals to the number of its columns. And it just means that we need to make all the column vectors of A are linearly independent. And actually, when we make the batch size of the matrix large enough, it is almost impossible for the vectors to be linearly dependent. That problem is why these two ranks are equal. We know that the rank of a matrix plus the dimension of its null space equals to the number of its columns. So we get these two equations. So if we want to prove these two ranks are equal, we just need to prove that the dimension of these two matrices are equal. And here comes the proof. If an x satisfies this expression, then we can multiply the transform of x in the left side of both sides of the equation. And after a series of calculation, we can get this one. And obviously, ax should also equal to 0. And that means the x here is also in the null space of the matrix A. From the other side, if an x satisfies this one, we only need to multiply the transform of A in the left side of the equation, and we can get the transform of A multiply x equals to 0. So we can find that the null space of these two matrices are the same, and we get the rank of these two matrices are equal.
And target Y. First, we arrange our data into matrix form. We create the design matrix X and the target vector Y. As you can see here, the X is 1, 1, 2, 1, 3, 1, and 4, 1. If for the Y, 2, 4, 7, and 7. The first column of X is the X values. The second column is all ones. This is for the bias term weight 2. Y is simply the Y values from our data. And then the next step. Next, we compute X transpose times X. Then we get this result, 30, 10, and 10 and 4. This small 2 times 2 matrix comes from multiplying X transpose by X. It's a key part of the normal equation we saw earlier. And then step 3, calculate X transpose times X and then inverse. The inverse exists because X transpose X is invertible. And it's invertible because our two columns in X are linearly independent. As you can see here, this is the result after being inversed. And then step 4. For the final solution, now we use the least square formula. W equals this X transpose X times X and then inverse times X transpose times Y. And then we get the result W equals 1.8, 0.5 here. Our best fit line is y equals 1.8x plus 0.5. How did we get this? Because of this numbers around here.
The power of linear algebra in modern science. First, core concept. The least square problem is the mathematical backbone of fundamental AI algorithms. And this is true because linear algebra is the heart of regression and classification and everything related to that. AI work with matrices. Second, linear algebra tools. We leverage essential concepts, vector space, orthogonality, matrix transpose, and inverse, etc. We use all of this in AI and in other science too. 3. Cross-learning outcome. We have successfully achieved CL3, explained the application of linear algebra cogently and professionally is appropriate language that everything and everyone in the world can read and try to solve and explain. It's just a modern language and it's worldwide. 4. Broader signification. Linear algebra provides the elegant and efficient framework for solving complex prediction, modeling and optimization problems across science, engineering, and AI, and everything. Someone said, from civil engineering to machine learning, linear algebra is the universal language that enables us to understand, model, and solve the complex systems that shape our world. Because all the systems in our worlds are based in math, especially in linear algebra. And we try to do math modelization for that, and there is a lot of competition. Something like MCM, ECM, it's every year, and we use linear algebra to solve and modelize these problems into math equations. Thank you so much. That was our presentation about the application of linear algebra in science and engineering. If you have any questions, we welcome your questions and feedbacks about the least squares problem and its application in AI. Again, it was presented by us, Kenji Terencio, Zanjinu, and me, Lashi Muhammad Amin, for the class of linear algebra in the academic session 2025-09. Thank you, goodbye.